Hello friends, in this part I want to talk about Heisenberg's uncertainty principle, wave packet and gamma ray microscope experiment. What is the statement of Heisenberg's uncertainty principle? It is impossible to measure both position and momentum of a particle at any time with infinite precision. Product of uncertainty in position, which is x, and uncertainty in momentum, which is delta p, is always greater than or equal to h bar by 2, where h bar is Planck's constant, h bar is equal to h by 2 pi, and h is equal to 6.6 into 10 to the minus 34 joule second, and we have delta x, delta p is more than equal to h bar by 2. Now, what is the meaning of precision and uncertainty? When we measure position x, different x values are randomly distributed about their average values. Precision refers to how wide is this distribution. Now, this is important. Precision refers to how wide is this distribution. We are measuring x and we are not getting the same values of x always. There is a distribution. Infinitely precise measurement of position x means width of this distribution is 0 and uncertainty delta x is 0. Similar arguments holds for precision and uncertainty in momentum measurements. So, I have defined what is uncertainty. According to classical physics, we can design experiments for simultaneous infinitely precise measurements of x and p. It can be a challenging task, but not forbidden by laws of classical physics. Quantum physics via uncertainty principle forbids such measurements because delta x is equal to delta p is equal to 0 condition violates uncertainty principle. So, this is the difference between classical physics and quantum physics. In classical physics, there is no bar. Theoretically, there is no bar that delta x and delta p both can be 0 and hence their product is 0. Now, it can be difficult to measure experimentally to such situations where we have both uncertainties 0, but not forbidden by the laws of classical physics, but it is forbidden in quantum physics via uncertainty principle. This is an important thing to remember. However, uncertainty principle allows either delta x is equal to 0 or delta p is equal to 0, but at a price. Suppose we prepare a one particle system corresponding to delta x is equal to 0 by letting it pass through a very narrow slit. Then delta p is more than equal to h bar by 2 into 1 by delta x, and this makes delta p infinite. Such experiments force completely uncertain momentum values on the particle. Similarly, if a beam of particle each having fixed energy, which is p square by 2m, is made ensuring delta p is equal to 0, then delta x is more than or equal to h bar by 2 into 1 by delta p, and this makes delta x infinite. Such experiments force completely uncertain position values on the particle. Now, it so happens that nature simply does not allow any experimental setup where both delta x and delta p are 0 at the same time. We just cannot have both 0 at the same time, which means we just cannot measure both of them infinitely precise. Both uncertainty cannot be made equal to 0 at the same time. Now, what we do in physics? We make measurement on system, check if the behavior of system is consistent with existing theory, if not, modify theory and design new experiments to test the modified theory. This is the spirit of physics. Now, in diffraction of electrons by single slit and in gamma ray microscope experiments, we can measure precise position of electron. We will show that this act forces completely uncertain momentum values on electrons. Conversely, these experiments permit a very precise momentum determination of electrons, but then they force completely uncertain position values on them. These results are quite inexplicable from classical physics, but are in complete conformity with quantum physics via Heisenberg's uncertainty principle. So, essentially I am saying that the experiments which we now consider, and these are the diffraction of electron experiments and gamma ray microscope experiments, and we will try to see that how they are consistent with the Heisenberg's uncertainty principle. Now, we can understand Heisenberg's uncertainty principle using de Broglie hypothesis. De Broglie relation associates a wave having wavelength lambda with a particle moving with momentum p such that lambda is equal to h by p. A monochromatic wave is not a useful description of a particle because it has infinite extension in space. A particle, we know, should have finite extension in space. Now, earlier I talked about the wave packets. Now, the wave packets means a particle has a finite size and so have wave packets. So, we said that the particle wave packet is a good description of the particle. Then, by superposition of large number of waves differing in lambda values, we can form a wave packet. Such a wave packet is made up of many waves differing in propagation constant k values as k is equal to 2 pi by lambda. It can be shown that the length of wave packet delta x is related to the spread of k values delta k forming the wave packet by the relation delta x delta k is more than equal to 1. This is a important relation. We have a packet is a size delta x. This packet is made of so many waves. Each wave has lambda. So, spread of waves, spread of lambda means spread of k, and spread of k is delta k. Now, it so happens that these two spreads, spread of the wave packet which is delta x, spread in delta k is always more than or equal to 1. Smaller is the length of the packet delta x, more is the spread in k values delta k which form it. In the extreme limit, when delta x goes to 0, delta k goes to infinite, and we have waves with infinite spread in k values and a extremely narrow packet. You see the diagram. In this diagram, delta x is the length of the wave packet and delta k is the spread of the k values around the mean value k 0, and these spread delta x and delta k satisfy the relation delta x delta k is more than equal to 1. So far, no quantum physics was involved. So, the quantum physics enters via de Broglie relation lambda is equal to h by p. Wavelength is related to propagation constant k and k is equal to 2 pi by lambda. With this, de Broglie relation becomes p is equal to h by lambda is equal to k h bar, where h bar is h by 2 pi. This is a connection between wave property parameter k and particle property p of the particle. We talked of wave particle duality. So, there should be connection between what is a particle property and what is a wave property. Wave property is in k, the particle property is in p. P is the momentum, k is the propagation constant. So, de Broglie relation is just a relation between these two properties, p is equal to k h bar. Spread in k values are now related to spread in momentum values, delta k is equal to delta p by h bar. Remember, we have p is equal to k h bar and h bar is a constant. So, delta p and delta k are related by delta k is equal to delta p by h bar. We denoted length of wave packet associated with particles delta x because particle can be anywhere inside this packet and making its position uncertain by the amount delta x. Because we talked of the uncertainty. What is uncertainty? Uncertainty means as far as it is in the packet, we do not know where it is in the packet. Size of the packet is delta x. So, naturally the uncertainty in x is delta x. We have shown that delta x into delta k is always more than equal to 1, and as I told you, there is no quantum physics in it, but you supplement it by the relation delta k is equal to delta p by h bar, and we get the relation delta x delta p is more than equal to h bar, and this is the uncertainty relation. So, you get the uncertainty relation by a classical result delta x delta k is more than 1 supplemented by de Broglie hypothesis. Now, I must say that this is not a proof of uncertainty relation, this is not a proof, but we just have a feel of it, and the feel means the product is going to be more than certain value, it is not 0, this is important. In the classical physics this can be 0, in the quantum physics there is a lower limit, and this lower limit is like h bar. Experimental setup which measure position precisely like delta x goes to 0 involve working with wave packets having large spread of k values delta k goes to infinity, and hence large spread of momentum values delta p goes to infinity, making simultaneous measurement of position and momentum with infinite precision an impossible task. Now, another experimental setup which measure momentum precisely delta p goes to 0 involve working with large wave packets having large spread of x values delta x goes to infinity, again making simultaneous measurements of position and momentum with infinite precision an impossible task. Between these two extremes, product of uncertainties in x and p is bounded from below, and there is no way of making any measurement which violates the inequality delta x times delta p is more than equal to h bar by 2. This is a very fundamental result, that this uncertainty product is bounded from below. You can't make this product less than this, it has to be greater than this, unlike classical physics which admits this to be 0. In classical physics we can have delta x delta p equal to 0, which is impossible in quantum physics, it is always more than h bar by 2. Now, I consider diffraction of electron through a slit. You see the diagram, here you have monochromatic parallel beam of electrons each with momentum p incident on narrow slit of width delta x at a distance x from origin as shown in the diagram. What is observed on screen is a diffraction pattern with this central band of maximum intensity together with dark and bright bands of decreasing intensity on either side. So, what we have from de Broglie relation, lambda is equal to h by p, this is what is the de Broglie relation, and from diffraction theory we have sin theta is equal to lambda by delta x. It is just optics, because we say that electrons are diffracted, and from the diffraction we have result sin theta is equal to lambda by delta x. So, it is clear that delta x is equal to lambda by sin theta is a measure of uncertainty in position of electrons. Further, if uncertainty in px is delta px, we can write delta px is equal to p sin theta is equal to h by lambda sin theta. This is obvious from the diagram which I made, that the uncertainty in px is just delta px is equal to h by lambda sin theta. and from these two relations we immediately have delta x times delta px is equal to h. Now, again this is not exactly uncertainty relation delta x delta px is more than or equal to h bar by 2. Now, this is because delta x and delta px have not been defined precisely. I have just told you it is the width, but how do you define the width quantitatively? I have left it. So, they do not agree quantitatively, but what is important is that this product is not 0. This is the thing, that the product of uncertainties is not 0. Whether it is h or h bar by 2, it is a different matter and it is related to how you define the uncertainties, but it is not 0 as it was in classical physics. Attempts to measure x precisely force high uncertainties on measurement of px. Now, consider another experiment which is called the gamma ray microscope. In this experiment, according to laws of optics, image of electron formed by a microscope will not be a point image, but a diffraction pattern with a central bright fringe surrounded by a alternate dark and bright rings. Now, this is I would say that it is a result from optics. When we image any object, then a point object does not form a point image, and it is always a sort of diffraction pattern with a slightly, you can say, the central bright fringe, it is there. So, this is just a result from the optics, and we will see that delta x, which is the width of the central maximum, is determined by angular width alpha of the objective lens of microscope and wavelength of light scattered into it, and we have delta x is equal to lambda prime by sin alpha. It is still in optics. What you are saying is that when you observe something by microscope, maybe a point object, then you have to have a width delta x, which depends on lambda prime, which is the wavelength scattered into it, and the aperture alpha via sin alpha, and you have delta x is equal to lambda prime over sin alpha. Now, remember that momentum of incident and scattered photons are h by lambda and h by the prime respectively, and electrons suffer a recoil in the scattering of photon. You must recall we had the Compton effect, and the Compton effect told you that there is also a momentum associated with the photon, and essentially a photon is being scattered. That means, the photon carries a angular momentum which is h by lambda. So, the momentum carried by the incident photon is h by lambda, and the momentum carried by scattered photon is h by lambda prime. Now, you just apply laws of conservation of momentum for electron plus photon system when the scattered photon makes angle phi with the vertical, and you have p x is equal to p cos theta is equal to h by lambda minus h by lambda prime sin phi. This is just, you say that what was the momentum before, what is the momentum afterwards in the x direction, you equate the two. And now you notice that phi varies from 0 to alpha. Therefore, uncertainty in momentum of electron is delta p x is equal to h by lambda prime sin alpha. This is a result. We have shown that the uncertainty in the momentum delta p x is h by lambda prime sin alpha. We had earlier showed what was delta x, and was delta x was lambda prime by sin alpha. You put them together and you have delta x delta p x is equal to h. Again, it is not exactly Heisenberg's uncertainty principle, but it is clear that the uncertainty product cannot be made equal to 0. So, essentially gamma ray microscope is a device which tells you that no matter what you do, you cannot make this product 0, it is bounded from below, and what we have seen is delta x delta px is like h, which is not 0. Now, delta x is this and delta px is this, as we have shown earlier, and attempts to measure position accurately by making delta x small are accompanied by large delta px. You see how you will make delta x small? You will make lambda prime small, you will make alpha small, you will make lambda prime by sin alpha small, but then you see in the delta px we are just the inverse. So, if you make lambda prime by sin alpha small, then sin alpha by lambda prime will be large. So, any attempts which make delta x small would lead to making delta px larger. So, this is what is that you attempt to measure position accurately and you land up with delta px very large. You cannot measure delta px accurately if you measure delta x accurately, and conversely if you want to measure delta px accurately and for that you use large lambda, then it is accompanied by large delta x. So, the point is that you just can't have both these measurements precisely, and the gamma rays have been chosen because locating position of electron in an atom and atom size is like 0.5 angstrom with uncertainty equal to 10% of atomic size requires lambda is equal to 0.05 angstrom, which is in the gamma ray range. You might wonder why gamma ray? Gamma ray is there because you want to measure the position of electron in an atom accurately. So, you need to have a small wavelength, and that is why you have a gamma ray microscope. We now consider applications of uncertainty principle, and first is non-existence of free electrons in the nucleus. In beta radioactivity, electrons are emitted by the nucleus. One may think that free electrons reside inside the nucleus before they are emitted, but using uncertainty principle we can show that this is not the case. After all, what is happening is that electrons are coming from the nucleus. So, you would think that electrons could be inside the nucleus, and this uncertainty principle help us decide that this is not the case, because the nucleus size is of the order of 2 into 10 to the minus 14 meter. Maximum delta x for electron is 2 into 10 to the power minus 14 meter if it is in the nucleus. It is very obvious, because if the electron is in the nucleus, then uncertainty in x is going to be of the order of the size of the nucleus, and then this fixes the minimum of delta px via uncertainty principle, and we have delta px is h by delta x, which is like 5.3 into 10 to the minus 21 kg meter second inverse. With the p minimum value of momentum is p minimum, and p minimum has been fixed already. So, from this we can calculate E minimum, which is the relativistic kinetic energy, and from the relativistic kinetic energy we can find out the kinetic energy by the relation E minimum minus m0 c square, where m0 c square is the rest mass energy, and with these calculations we land up with the kinetic energy being equal to 9.4 MeV. Now, the point is that if you say that the electrons are inside the nucleus, then we have that they should have the kinetic energy which is 9.4 MeV, but observed kinetic energy of electron is found to be much less, and the maximum kinetic energy is about 4 MeV. You see the difference, 4 MeV is the observed value, and what is predicted via uncertainty principle, if you assume electron to be inside the nucleus, is 9.4 MeV. So, it is clear that the free electrons cannot be inside the nucleus. So, it is one applications of Heisenberg's uncertainty principle which help us decide whether or not the free electrons exist in the nucleus in the beta radioactivity, and we have emphatic no, that no, the free electrons cannot be there inside the nucleus as far as the beta activity is concerned. The second is the size of the hydrogen atom and its ground state energy. Now, orbit radius is r, maximum uncertainty in position with respect to nucleus is r, because we have to estimate the uncertainty. If you say that it is orbit radius is r, then it is natural to associate the maximum uncertainty which is like r, because if I say that you are in this room and the width of the room is like 10 meters, then obviously my uncertainty is going to be 10 meters, because if I am in a room, then uncertainty is just 10 meters. So, we have a method of estimating the uncertainty in position. Next, what is the minimum uncertainty of the momentum is h by r, because h bar by r, it is by uncertainty principle, because it says the product is of the order of h bar. Then with this we have the minimum momentum p is equal to h bar by r, because you see we have two things, one is the uncertainty, another is the momentum, and we are making the argument that at least the momentum should be of the order of the uncertainty. This is the argument. So, once you have estimated the uncertainty, you have the estimate of the momentum as well, and you put these two in the total energy, and you have the expressions for total energy E is h bar square upon 2 m r square minus E square upon 4 pi epsilon 0 r, where the first term is the kinetic energy, second term is the Coulomb attraction energy. All that we need to do now is that you minimize this energy with respect to r, and you insist that dE by dr is equal to 0, and the second derivative is more than 0, and you have orbit radius r is equal to epsilon 0 h bar square upon pi m e square, and the ground state energy E is minus 13.6 electron volt. So, you see we have estimated the orbit radius and the energy via uncertainty principle, and these are in accordance with the experimental results. Now, the question is why the effect of uncertainty principle is not noticed in daily experience or in classical physics. This is related to smallness of Planck's constant h is equal to 6.6 into 10 to the minus 34 joule second. Let us estimate delta x and delta p for a dust particle in normal laboratory situation. Delta x is 10 to the minus 5 meter seems reasonable. Many times it can be much more. Now, you see mark the figure, delta x is 10 to the power minus 5 meter. This is the uncertainty in x. This is very reasonable. 10 to the minus 5 meter is a very small thing. So, we should estimate that we cannot do much better. And then suppose we have a particle with mass 1 milligram, and it moves with the velocity 1 meter per second, and the precision of velocity measurement is 1 part in 10 to the power 6. Now, again this is also reasonable. You say that you are having a precision of 1 in 10 to the power 6. It is a reasonably good assumption. You are measuring velocity better to the part of 1 in 10 to the power 6. What does it mean? It means that delta V by V is 10 to the power minus 6. This is the thing. It is not bad. You are measuring up to 1 part in 10 to the power 6. You put V is 1 meter per second, you put mass as 10 to the minus 6 kg pertaining to the dust particle, and you have delta P is equal to m delta V is 10 to the power minus 12 kg m second inverse, and delta x delta P is 10 to the power minus 17 joule second, and it is 10 to the power 17 h bar by 2. You see, now it is very interesting figure that this uncertainty product is 10 to the power 17 times the minimum which is expected from the uncertainty product. Now, we have already stressed our limits and still this product is much above the limit h bar by 2 set by uncertainty principle. Uncertainty principle does not allow the product delta x delta p to go below h bar by 2. In our daily experience and in classical physics, this product is always much above this limit and uncertainty product is not worth caring. This is the point. Why should we care about this? We are already in the regime where this product is 10 to the power 17 times the minimum. So, if it does not go to 0, let it be, I do not care. This is the point, and this is the point, this is the reason why uncertainty product does not play a crucial role in classical physics. Now, can we ignore uncertainty principle in understanding behavior of electrons in hydrogen atom in ground state? No. We can show that delta x delta p is equal to h bar by 2, which is the lowest value allowed by uncertainty principle. Electron behavior is explained in terms of wave pattern of confined electron wave. It has fixed energy, but spread in x and p values consistent with uncertainty principle. So, the uncertainty principle is important when you are considering the behavior of electron in hydrogen atom in the ground state, because now there this product is of the order of h bar by 2. You contrast it with the classical physics where it was 10 to the power 17 times h bar by 2. You can see the difference. So, we cannot ignore uncertainty principle in understanding behavior of electron in hydrogen atom in ground state. So, today we have discussed the uncertainty principle. It is a statement, and we have seen that no matter what you do, this uncertainty product cannot be made equal to 0, unlike the classical situation where you can make this product 0. And we have seen how experiments like electron diffraction experiment and gamma ray microscope experiment are consistent with the uncertainty principle, and we have also seen why this uncertainty principle is not important in our daily life and in classical physics, but it is very important when you consider the behavior of electrons in hydrogen atom. Thank you.